Welcome to Solutions in Stoichiometry. Now that does imply that we're going to be doing some stoichiometry problems using solutions. So one of the first things that we're going to have to conquer is how do we measure these solutions? Well, your brain might immediately go to using a balance because that's basically the big tool that we've been using all year so far in lab. So what would happen if I just put a solution on top of the balance? Well, clearly nothing good. Our balance would probably fry. And you're probably thinking, well, that's pretty silly. Why don't you put it into a beaker? Well, that would be lovely, but then remember on top of the balance, we have a couple things going on. We would have a beaker, we would have the water that's in the solution, and the chemical itself. So that leaves us with a pretty big question. How do you know how much of the total mass belongs to just the chemical? There must be a way. In stoichiometry in general, what we need to make sure of is that we need to know how much exactly of just a pure chemical goes into this chemical reaction so that we can know how much of any given product we're actually going to make. Now, unfortunately, what that means then for the use of a balance with solutions, it's just not the best tool for the job. So there must be some other way of how I communicate how much stuff is actually inside of a solution. And in fact, there's a couple different ways. Let's start qualitative. So here on the screen, I have a couple different glasses of a Kool-Aid mixture. And let's start with the one all the way over on the left-hand side. This one would taste extremely terrible because it's really, really weak. We call this solution dilute. It's a dilute solution of Kool-Aid. Well, what about the solution all the way on the far right? We would also say that this one probably tastes pretty terrible because it's so terribly strong. We call this solution concentrated. A couple other words that you're going to need to be familiar with, such as what do we actually call scientifically the stuff that we pour in that creates this lovely gradient? The Kool-Aid itself is the stuff that's being dissolved. We call the stuff that's being dissolved the solute. And then the water that we use to make our Kool-Aid, it's the stuff that's actually doing the dissolving. We call the solvent. Now, a couple things that you really need to make sure that you have in your head is that a dilute solution doesn't have very much stuff dissolved in it. So the official pinky in the air type way of saying that was it has a very small amount of solute given a very large amount of solvent. A concentrated solution, and you can see very clearly on the screen, has a lot of stuff dissolved inside of it. We would say that this has a large amount of solute for the given amount of solvent. Well, all of this is really lovely, but we need some numbers. Unfortunately, when we go back to a stoichiometry problem, I still need to know how much of one pure substance I have going into the reaction so that I can figure out how much is coming out the back side. Well, generally speaking, how do we communicate how much of that specific chemical we have? Well, in all the calculations that we've done so far, when we've had, say, grams, the very first step of our problem is we convert it to moles. So, gee, I wish there was a way of communicating how many moles was in a solution, because then we could actually do something with stoichiometry. Enter molarity. Molarity is this way. It is a way of communicating how many moles of material we have dissolved inside of our solution. So just kind of take a look at this little bit of picture here. A dilute solution would only have a little bit of material dissolved inside of it, whereas a concentrated solution has a lot of it. Well, what if I could actually measure those bits? So molarity really kind of communicates how much solute, the stuff that's being dissolved, we have as a function of how much solution we're dissolving it into. We really communicate the amount of the material being dissolved in the form of moles, and we're going to communicate the amount of solution that we're using, how we measure any liquid, not with grams, but with liters. Now, these two things combined give you molarity. Molarity has its own little symbol when you go to finish up the calculation and display your data. We actually just shorten it to big old capital M. So let's do kind of an example problem. Say, for example, I'm making a solution and I use 3 moles of solvent and I put that in 1 liter of solution. If I actually throw that in my calculator, I'd find that the answer is still 3. So my answer I would display as 3m. Now when you're talking in words, like between, say, lab partners, or if you're communicating this number to me, we would call this a 3 molar solution. Just like it was like a tooth, which is kind of weird, I know. But it really doesn't mean that your solution is made of teeth. It's really just a 3 molar solution. And I really kind of don't understand why scientists are so obsessed with all of these different weird names of things like moles and molar. But anyway, I digress. Let's get back to an example problem. So here's our example problem. What is the concentration of a solution that's made from 5 grams of sodium iodide in enough water to make 15 liters of solution? Well, first thing I'm going to have down on my page would be the actual formula for molarity, moles of solute divided by liters of solution. And then I'm going to go back to my problem and see what I'm given. First thing glaringly obvious to me would be that it actually tells me I have 15 liters of solution. Well, I'm just going to slam that right into my cute little calculation. So I'm going to get my new little calculation started. 15 liters of solution is now on the bottom. The other thing that I noticed was that the problem also gave me the amount of 5 grams of material. And I would really love to just put that right at the top of my little fraction over here, but if you'll notice, my units don't match, and they really need to match before you go ahead and plug that in. That means I have to convert it. So we'll get ourselves ready with some field goal posts, and I'll take that number that I was given, and I'll put that over 1, 5 grams of sodium iodide divided by 1. Remember that your unit and your substance crosses down to the bottom of the next box, and we would get this number, the molar mass of sodium iodide, from the periodic table. I add the mass of sodium and iodine, and I find out that it's 149.89. Now we're allowed on the top of this next fraction to put in its place 1 mole. Time to plug and chug. I find that with good significant figures, 2 in is 2 out, I would get 0.033 moles of sodium iodide. And it's in fact this number that I want to plug and chug into my problem, because now the units match. So I go ahead and I plug that in and solve it, and I find out that my final answer is 0.0022 molar. And again, you want to make sure you have good significant figures. When you're dividing, it's the fewest number of significant figures that you had that you were plugging into your calculator. So let's go back to this cute little equation here. Now, not all problems are going to be exactly like the one that I gave you, but they're all pretty similar. Some problems give you moles and liters in one way or another. Some problems will give you grams that you have to convert to moles. Some problem will give you milliliters that you have to convert to liters. Other problems are even more twisted. Maybe they'll give you moles and molarity, and they'll ask you to solve for the liters. Some problems are even wackier, where they'll give you the molarity and the liters and ask you to solve for moles. But what this all boils down to is you using your head, being aware of the data that they give you in the problem, and boiling it back to these 3 units, moles, liters, and molarity. And essentially, my favorite style of problem, plug and chug. Try some out. Good luck.